All right, y'all. Hopefully at this point you have read the entire lecture and all of the lecture notes beneath the PowerPoint slides related to one-way ANOVA, and you understand what a one-way ANOVA is, when you use it, and what it does mathematically, at least have a conceptual understanding of that. Now we want to apply that understanding and actually work one out beginning to end, okay? And so I want to work this problem with you, and then I also want to briefly look at the spreadsheet that is laid out for your homework so that you can see how these numbers that we are calculating here on the board would fit into the cells in the homework spreadsheet, okay? So our in-class example for a one-way ANOVA between subjects is that a researcher wanted to determine the effects of 3 different drug dosages on the number of errors committed by rats in a maze. They randomly assigned 30 rats to one of 3 treatment groups, placebo, 10 milligrams, and 20 milligrams, tested the hypothesis that there is no difference between the groups at an alpha of 0.05. And here is your data, okay? Now, the very first thing you're always going to do when you're approached with any example problem is set up your data in your Excel spreadsheet. Please, as you're doing homework, use the spreadsheets that are provided for your homework directly below your homework, all right? Now, here is our data for the for the one-way ANOVA. And here you can see I've got the data for the placebo group, the data for the 10 milligram group, and the data for the 20 milligram group in its own column. You'll also notice that I combined all of the data together and put it in one column. You know, this isn't 100% necessary to do this because the total sum of squares is not really used in the ANOVA until you get to the effect size. And you can just add the between and the within sum of squares to get the total. However, then you don't know for sure that your total is right or that your between or within is right. I always do the total sum of squares because I find that is an excellent way to check my work. Because if my between sum of squares and my within sum of squares add up to my total sum of squares, then I know I've done my math right all the way through. Also, you know, it's really easy to calculate a grand mean from the mean for placebo, 10 milligram and 20 milligram when they all have the same n like these do, because I could just add up the 3 means and divide by 3 because there's an equal number of participants. However, not in every problem that you do, this is not always going to be the case. Sometimes you'll have unequal n's, which you can still do a weighted mean, but it becomes a much more complicated process to calculate the grand mean or overall mean for all of the data set, okay? So the first thing that we need to do when setting up ANOVA data is, just like we did for the independent t-test, calculate a mean for each group and a sum of squares for each group, okay? So let me do that here on the Excel sheet, and then we'll transfer these numbers to the board so that we can work this problem all the way out, beginning to end. So I'm going to sum up my values, and I'm going to divide by the number of values. That gives me a mean of 2.6 for my first, for my placebo group. So equals every score minus that 2.6. Then I'm going to square all of those values. And then I'm going to add them up. And there is my sum of squares for the placebo group, okay? I'm going to do the same thing for my 10 milligram group. Their mean is 3.8. I'm going to subtract that from every bit of the data for that group. And then I'm going to square those values. And then I'm going to add them up for my sum of squares for the 10 milligram group. Now I need to do that for my 20 milligram group. And I'm going to get a mean for that group of 5.1. We'll subtract that mean, 5.1, from every number in the data set. I'm going to square those values. And I'm going to add that up for the sum of squares for the 20 milligram group, okay? Now I'm going to do that for all of the data. I'm going to do an auto sum for every bit of the data, and then I'm going to do an overall mean. The overall, we're dividing this by 30 because there are 30 participants in all three groups combined. And the grand mean, or the overall mean for all data, is 3.83. So I'm going to subtract that from every number in the data set. I'm going to scroll that down. And then I'm going to square all of those values. I'm going to scroll that down. And I come up with a total sum of squares for the dependent variable number of errors in the maze of 124.167, okay? Now here, you might want to jot these numbers down on a piece of paper because you will actually be entering them into the formulas on the second page of your spreadsheet that I will show you after we do. I'll work this out on the board. But I'm going to jot these numbers down on the board so that I have them right here at my ready as we are looking at and working through the formulas, okay? So my big N is going to be 30, because that's how many I have in all three groups combined. But that makes my little n 10, because there are 10 in each group, okay? Now I have the mean for the placebo group, and actually let me not confuse you by using X bar, because your books use the n now. But mean for placebo and sum of squares for placebo. We need the mean for the 10 milligram group and the sum of squares for the 10. We need the mean for the 20 and the sum of squares for the 20 milligram group. And then we need our grand mean and our sum of squares total. So I've got 2.6 here, 42.4, 3.8, 17.6, 5.1, 32.9, and then 3.83 for the grand mean, and total sum of squares equaling 124.17, okay? And our alpha level as established in the problem, 0.05, okay? All of this information will be important as we're working through this, all right? So let's come back real quickly and look at the in-class example. Now, the first thing we want to do are our 4 steps of hypothesis testing. The first step would be to state our hypotheses. So we want to read the problem to figure out what that is. It says test the hypothesis that there is no difference between the groups. So here we are not looking for a directional greater than, less than in our hypothesis. We are just looking for equals and not equals because we're just looking to see if there is a difference. We're not specifying which group and what that difference would be, okay? So step 1 for hypothesis testing. State my hypotheses, my null hypothesis, would be that all of these means are equal. So the mean for the placebo group is equal to the mean for the 10 milligram group, which is equal to the mean for the 20 milligram group, okay? Now my alternative or research hypothesis then would be that these means are not equal to one another. Now, step 2 is to determine what the critical value for F needs to be in order to reject the null, okay? So in order to determine that critical value, we need to know what our degrees of freedom are. Degrees of freedom between is going to be equal to K minus 1. K is the number of groups. So here our degrees of freedom between is 2, or sorry, it's 2, but it's 3 minus 1. 3 minus 1, which equals 2, okay? Now we also have our degrees of freedom within. And that is going to be equal to N, big N, minus K. Our big N is 30 minus K, the number of groups. We have 27 degrees of freedom within. And the alpha was 0.05, okay? We take all of that information to the chart in the back of our book that I have printed off, so for easiness in these videos, but you need to flip to the back of your book, to the chart for Oneway ANOVA, critical values for the analysis of variance, the F-test. And your degrees of freedom for the numerator, the between, goes across the top. The degrees of freedom within, or for the error, goes down the side. So we follow the top over to the number 2. We follow the chart down the side to the number 27. And then we choose the critical value that goes along with an alpha level of 0.05. And we're going to find that the F critical value then for this study is 3.35. So FCV. That just stands for critical value. That means that's what we have to exceed in order for us to reject the null hypothesis, okay? So FCV in this case is going to be 3.35, okay? Now, step 3 is where we get into some hairy, scary math. But it's not scary, it's just a little hairy, okay? I promise it won't be too bad. You just have to follow all of your steps and all of your formulas. So I really encourage you that once you have these numbers all set up, that you go back to your PowerPoint and you scroll to the slides. Excuse me, I'm getting dry. That have your formula on them, okay? Now, the sum of squares total, we don't need to actually calculate. We already calculated that, 124.17. But again, this is going to let us check our betweens and withins to make sure they come out right, okay? So, the whole point of ANOVA is that that's why we call it analysis of variance. Because we are analyzing the variance and partitioning it into 2 separate parts. Between subjects, or between groups, I'm sorry, not between subjects, but between groups, which is the differences between the means in each group as discussed, in the notes for the slide. And so literally it's the mean for every group minus the grand mean. Then we square that value, multiply it by the number of participants in that group. And once we've done that for every group, we're going to add those together. But basically what the sum of squares between is analyzing is the variance between the means of the groups, okay? That is what we would consider treatment variance. And we consider this difference to be because of the levels of our independent variable, which in this case is drug dosage, okay? So let's come over to the board here and do this, okay? The sum of squares between is literally going to be equal to the mean for group 1, 2.6, minus the grand mean of 3.83 squared, times n, which is 10, plus, do this for the next group, the mean for the 10 milligram group, 3.8, minus 3.83 squared times 10, plus the mean for the fourth group, 5.1, minus 3.83 squared times 10, okay? Now, in the Excel homework formatted spreadsheet, it shows you this with blanks in it, and you've got to fill in the blanks, or actually, rather, you're not going to fill in the blanks. You're going to replace the blanks with the correct numbers. And then it's going to literally show every step of the process. So once you've done this, the first thing we do are parentheses, right? And then we do exponents, and then we multiply. And so we're going to show the math for every step of the way so that when we make mistakes, we know where we've made those mistakes, okay? So here are some of the squares between, and I've already done the math really quickly on paper so I can make this a quicker process. But that is going to be, this one here is negative 1.23 squared, again times 10, plus negative 0.03 squared times 10 plus 1.27 squared times 10, okay? So now we want to square those values. So I'm going to end up with, for the first group, 1.51 times 10 plus 0.0009 times 10 plus 1.61 times 10, and that's that. And then I'm going to have 15.1 plus 0.009 plus 16.1, and all of that together is going to equal 31.2. Okay, so that is the sum of squares between, all right? Now, the sum of squares for the error, or the within sum of squares, and I do want to just talk about on this video real quick, in the between subjects ANOVA, and then again for the factorial ANOVA because it's going to be between subjects, within and error are synonymous, okay? Now, it will not be this way in the repeated measures ANOVA, because in the repeated measures ANOVA, we have to partition the error as well. And so this is just for our between and our two-factor. The within and error are synonymous. So if you see within, that means error. If you see error, that means within, okay? But let's go to the formula for that on our PowerPoint and just see that we know why we're choosing the numbers that we are choosing, okay? Notice that this is a formula you see a lot. Every score for the group minus the mean for the group squared added up. What is that? It's the sum of squares that we just calculated in Excel, right? And so basically what this formula is saying, this is the sum of squares for the placebo group, plus the sum of squares for the 10 milligram group, plus the sum of squares for the 20 milligram group. So this calculation is very, very simple once you've done your Excel sum of squares, because all this is telling you to do, add up the sum of squares for every group, period. Done, okay? So let's do that. Over here, our sum of squares for placebo, 42.4. Sum of squares for 10 milligram group, 17.6. Sum of squares for the 20 milligram group, 32.9, okay? Now, adding all of those together, I'm going to get a grand score of 92.9 for the sum of squares within, okay? Now, just a quick check for myself and my own personal edification here. 92.9 plus 31.2, which was our between, gives us 124.1. Look at there. The same as our sum of squares total, okay? That lets me know I did my math right. It lets me know before I move past this point that my sum of squares for the between and the within are correct. It's always good to know that, before you go on and do even more math with these numbers, okay? Now, we need to change these sum of squares. We're partitioning variance, okay? And remember, back to standard deviation time, that variance is the sum of squares divided by n. So we've got to adjust for that here at this point. And so we're going to take our sum of squares and we're going to divide by our degrees of freedom, okay, to create what we call mean squares. And those are the actual estimates of the variance, all right? So I'm going to have a mean square between, and it is going to be equal to my sum of squares between, which we calculated to be 31.2, divided by my degrees of freedom between, which is 2. So my mean square between is 15.6. Okay? Now I need a mean square within, or for the error. And that is going to be equal to the sum of squares for the error divided by the degrees of freedom for the error, which was 27. And that is going to give us a mean square between, or within, of 3.44. Okay? And then F, the actual statistic that we want to calculate, is equal to mean square between divided by the mean square within, and that is going to give us an overall F value of 4.53, okay? Now, step 4 for our steps of hypothesis testing is to decide, based on this statistic alone, would we accept or reject the null hypothesis? Well, our obtained F value of 4.53 is indeed greater than a critical value we found in the chart of 3.35, and so we are going to reject the null, and or we like to say reject the hoe in class. So if you were in my class, we'd be rejecting the hoe, which is always a smart thing to do, okay? Now, remember that just a statistic all by itself is not sufficient evidence for the American Psychological Association or journals that there's an effect of your independent variable, because n is a part of these formulas, and the bigger n gets, the more likely these things are to appear significant, even if they aren't. And so we have to compute what are called effect sizes to see what the overall effect of our variable is. There is also another analysis that we have to do in Excel, or that we have to do with ANOVA, that is called a post hoc test. We do post hoc tests because when we did a t-test and we found a significant difference, whichever group was significantly different, whichever group had the higher mean was, we would say, significantly higher. Or whichever group had the lower mean, we would say, my son is messing with me right now. He's behind the video camera. But we would say was significantly lower, because there were only two means. So if there were significant difference, guaranteed those two means were the ones that were different. Here in an ANOVA, if I find a significant difference, it could be that placebo is not equal to 10 milligram, which is not equal to 20 milligram, okay? That is possible. But it is also possible that just the placebo and the 20 milligram are significantly different, and the placebo and the 10 milligram are fairly equal, 10 milligram and 20 milligram fairly equal, and the only significant difference is here. There's no way to know that for certain with just a significant ANOVA. All the significant ANOVA tells us is there is a difference somewhere. We have to do what are called post hoc tests in order to be able to determine where those differences are, okay? So the next thing we want to calculate here are our effect sizes. So let's bring up the formula And I'm sorry, I guess I kind of skipped some PowerPoint formulas there as I was going. But you won't be able to do that. You'll need to look at these so you'll know, oh, this is my next step. Now this is my next step, okay? There's my effect size, or my F statistic. And now here is my effect size statistics. So we see for the eta squared, it's really easy. It's just the sum of squares between divided by the sum of squares total. So we will do that one here. Eta squared is the sum of squares between, which is 31.2, divided by the sum of squares total, 124.2. And that is going to give us a total overall effect size of 0.25, which if you will look at the bottom there of the slide, lets us know that that is a large effect, okay? So there is a large effect of drug dosage on a number of errors committed in a maze by rats when we use eta squared. But omega squared is a little more conservative of a value, so chances are we're going to get a moderate effect because there's no way if eta squared is 0.25 that omega squared will be that large. It is the more conservative. And so our eta squared literally is our sum of squares between 31.2 plus or minus the degrees of freedom between times the mean square within. Okay? And that is all divided by the total sum of squares plus mean square within. Okay? So that is going to give me 31.2. And again, we're going to be showing every step of our work, okay, in our Excel sheet. Minus 6.88 divided by 127.64. And I'm just going to go right here with this, which is going to equal 24.32 divided by 127.64. And that is going to give us an overall omega squared of 0.19, which we do see is a medium effect as expected instead of that large effect. Okay, this is the more conservative estimate. Although most computer programs, SPSS included, is going to give you eta squared, and most of the time when you see this reported in journal articles, you're going to see eta squared reported, okay? So that is our effect size statistic. And then the last thing we need to do here, y'all, is figure out which of these groups are different from one another. There is a large effect. It's a significant effect, and there's significant difference between our groups, but which groups are different? So we do what is called the, I'm sorry, let me come back to my PowerPoint. What are called post hoc tests. And HSD, we use the two keys, HSD. HSD stands for on a significant difference. Basically, it's saying how big does the difference, HSD tells us how big the difference between means has to be in order for us to reject the null, okay? Now, Q critical is the table value that we get from our textbook for the two keys HSD test. The mean square within is the mean square for our within groups or our error, and the n here is the number of subjects in each group. If you didn't have equal n, you would average the n's to determine what that small n is, okay? So knowing what those things are, let's go over here and plug them into our formula. HSD is going to first be equal to Q critical, okay? Q critical is in this chart in the back of your book. And it says the number of means across the top. We have 3 numbers of means. The degrees of freedom for within, or our error, is 27. Now notice that the chart goes from 24 to 30. You can't use 30 because 30 is more degrees of freedom than what we have. So we have to back up and use the value for 27, or 24, and that is at a 0.05 level, 3.53. So that is the first number that goes into our formula here. And that is multiplied by the square root of the mean square within, which is 3.44, divided by small n, which in this case is 10. So we have 3.53 divided by the square, or multiply, I'm sorry, not divided, but multiplied by the square root of 0.34, which gives us 3.53 times 0.58, which is 2.05, okay? So basically that's saying the difference between these means has to be at least 2.05 in order for us to consider those two groups significantly different. So then we've got to take and say, okay, well, the difference between the placebo group and the 10 milligram group was 1.2. Okay? And the difference between the 10 milligram group and the 20 milligram group was 1.3. The difference between the means for the placebo and the 20 milligram group was 2.5. And so yes, this was a significant difference, but no, these groups were not significantly different from one another. And when we write up our results section, we'll say that. We'll say, well, yes, we got a significant ANOVA result, and there definitely was an effect of the independent variable, but not until you got to 20 milligrams, basically. The only two groups that were significantly different from one another was the placebo group and the 20 milligram group. The placebo didn't differ from 10 milligrams. 10 milligrams did not differ from 20 milligrams, but rather, in order to show a significant effect, you needed to get 20 milligrams of the drug, okay, in order for that to show an effect, okay? Now, before we conclude this video, I just want you to see, and this will be online for you to look at as well, but how this example, if this example were your homework, what would it look like, okay? This is what the first page would look like. You're literally going to take your sums and, put them into these spots that'll be blank on your homework. You'll take all your data and then, there'll be blanks. In your homework spreadsheet, and actually, I don't think I brought that one up. Let me grab it real quick, just so that you can see that. You can see how all of this is just empty, okay? And on the second page, it's just empty. But you can use my in-class example, because this will be up on D2L for you to look at to see which numbers go in which places. And if you'll notice, the board there, and then look back at the screen at this Excel sheet. And as you're watching the video, you can pull up this Excel sheet, in a separate window, and just see how I transferred the numbers from my math into the blanks on the spreadsheet, okay? And this will be how you will be submitting your homework for every assignment, as well as how you will be submitting your work for the in-class portion, or the take-home portion, calculation portion of the exams. And so it's just a matter of, you can work this all out by hand, probably easier, and then take those numbers and plug them in. But again, you're going to have to show every step of the process, but the blank spreadsheet shows you that. It shows you each step of the process. So just plug the numbers in once you have them, and that is what you will submit to show evidence that you knew what numbers went where and how to calculate this all the way out. We know that you can push a button in a computer program and generate these results, okay? The point here is we want to know you know what numbers went into creating those results and exactly how the math was done to get you there. And so this is how you will show that for your homework. And so the first sheet is your sum of squares, second sheet will always be your formula, third sheet is your effect size, fourth sheet is your hypothesis or your post hoc, and all of those will be blank, and you will just fit the numbers in just like I did for the in-class example. That will be online for you to reference, okay? All right, that concludes our example of Oneway ANOVA. Happy math. Go do some homework. Y'all also don't forget, these assignments are lengthy. Don't wait until the hour before they're due to try to get them done. You won't have time. So, gauge how much time it'll take you after this first one, but definitely allow yourself ample time, at least 2 to 3 hours per assignment. All right? Have a fabulous day. Fun math.